Hello and good day once again. In the last videos, I've shown you how to convert a program from the IIS into the language of the Intel processor, which is used as the processor for the IBM PC. I've also showed you a demo program that is used to compute the n factorial, something which we have converted from the language of the IIS machine into the Intel Core I processor. Uh, In this, I've also shown you, by the way, in addition, the how to trace programs, create and trace programs using Visual Studio 2019. In this video, I'm going to show you how to convert a program that computes the grade using dWORDs into a program that computes the same values using floating point variables. Before we do that, let me introduce you to the structure of the IBM PC, or rather the Intel CPU. The Intel CPU is an advanced CPU which has two arithmetic units. Uh, Particularly, it has a 64-bit ALU and a 64-bit FPU. The main difference being that the ALU is now limited to perform arithmetic using integers or whole numbers, and the FPU being used to do arithmetic using floating point values or numbers with decimal values. Now, these two units are independent of each other, which means that the FPU has its own sets of registers, while the 64-bit ALU uses EAX, EBX, and so on, particularly EAX as the accumulator. The 64-bit FPU uses a stack system, okay, wherein the stack is used as the accumulator. In this case, we do not access the stack right away because we do not have a name for it. But we can access the value of the stack or its accumulator using normal loading and storing of variables. Likewise, we know that the ALU has flags registers, which is it uses for conditional jumps. Particularly, we have uh, the carry flag, the zero flag, and the sign flag, which we use for commands like jump if sign, jump if no sign, and jump if zero, and jump if above or equal, and so many others. So we have to remember that uh, the conditional jumps apply only to the ALU. It does not apply to the FPU. Before we start converting that program, uh, let us compare the instructions between the ALU and the FPU briefly. So when you use the ALU, you can use all arithmetic operations right away, which means that you do not need initialization. The FPU, however, needs to be initialized. The instruction to initialize the FPU is called finit. Initialize the FPU. Now, in terms of loading variables, in the ALU, we use the move instruction. Like, for example, if we want to move a variable from into its accumulator, we say move EAX variable. In the FPU, we say FLD variable, which means fload variable. It loads it to the FPU stack, which is used as its accumulator. When we store values to variables using the ALU, we say move variable EAX. And we have to emphasize that this movement is a non-destructive movement, which means that it will not destroy the source, which is EAX. On the other hand, the storing of variables in the FPU can be done using FSTP. The equivalent command is FSTP followed by a variable name. And we have to remember that this is a destructive store, which means that it will destroy the source, which is the CPU stack, or the or rather FPU stack, which is also its accumulator. The fact being that it's a stack, so it will pop the stack after it has stored the value. In terms of arithmetic, addition is done in the ALU using add EAX variable. In the FPU, you say fadd followed by the variable. Sub is done using sub EAX. In the FPU, we say fsub. If in the ALU we say mul, in the FPU we say fmul. Div is likewise done by using fdiv. Now, in terms of comparison, we use the CMP command for the ALU, where we say CMP EAX variable, which actually does subtraction, non-destructive subtraction between EAX and the variable. In terms of the ALU, we say fcom variable. It's also a non-destructive subtraction. But we have to follow it with FSTSWAX and SAHF. Why is that? Because the conditional jumps of the ALU will not apply with the FPU. Like for example, if you have a jump instruction such as JAE. Unfortunately, we do not have conditional jumps which uses the FPU. In the ALU, if you can say JAE, we cannot say FJAE because there's no such command or instruction in the FPU. However, we can do a trick by synchronizing the ALU flags register with the FPU flags. We do that by two commands. The first command is FSTSWAX. It transfers the FPU flags to the AX. And then we transfer the AH to the register to the ALU by saying SAHF. This transfers the higher part AH to the ALU flags. That is because that's the only part where they are compatible, and that's the only part which we need in order to do conditional jumps, because we already have the flags 0, sign, 0, and sign. Now, let us head over to our Dagler's class, where we have a grade computation program which uses dWORDs. We are going to convert this program into a version which uses floating points, because we know that grades are floating point values. It's not enough to use dWORDs. So let's head over to that code and take note of this for the moment. And then let us proceed to starting our Visual Studio in order to create an assembly language project. Okay. We do the normal process, okay, which we have done before. What we usually do is create a C++ empty project and later configure the files for assembly language. So once Visual Studio started, we head over to create new project. We click this, and then we make sure that the languages part, the language part is limited to C++. And then we choose empty project and we click the next button. We can give a name to the project. We can say, for example, in this case, I will name it GCF 10, grade computation with floats version 10. You make sure that the play solution box is checked, and then click the create button. Once that's done, the first thing to do is normally to remove the unneeded files. Okay? We click them, we choose them together and delete. So the three unneeded files or folders are removed. Then we configure our project by heading over to the project line, the second line of the Solutions Explorer. And then we right click and we set the build dependencies, build customizations. In here, we are going to make sure that the Masam box as its target is checked, not just chosen but checked, and then click OK. And then the next thing to do is to create our source file. So we do that by right clicking on the same project line, choosing add, and then clicking new item. Now by default we are pointing to a C++ file. We'll just have to rename our extension as ASM. You can also rename the file name itself, but make sure that the extension is ASM before clicking add. Before starting the code, you have to make sure that the type of our source code is macro assembler, Microsoft macro assembler. We do that by getting the properties. We right click and get the properties of source.asm and make sure that the item type is Microsoft macro assembler. And then we click OK. To make a long story short, let us copy the file, rather the lines that we have in our Moodle class, and then uh, arrange this and compile this in our Visual Studio. We copy this code and then we head over to our Visual Studio and paste the code from there. It's already working. We have tested this before. We can just remove the extra lines. If you want to know what the use of these lines are, you can look at the first two versions of or rather videos in our assembly language programming series. Okay, so we are removing the extra lines because our diggler site created the unnecessary lines and makes our code longer. Before we compile it, we first have to relocate two lines. The lines which assumes that the grade is passing, particularly in this case lines 30 and 31. We choose this and we cut two lines and transfer them to the beginning. The logic didn't change. The result will still be the same. What we want to do is to avoid using EBX in the middle so that we can retrieve the EAX also right away. We save before we continue. Now, if you are using Visual Studio 2022, the main difference is in this box, no? The Solutions Platforms box. You have to set this to x86 because for Visual Studio 2022, the default is x64. In this case, we are programming in 32-bit mode, so we have to specify that the platform is x86. Now, we transform line per line. Okay, you just have to comment out this line because this time we are going to use the FPU. So as I have said, we are going to initialize the FPU first using FPU init. And then the move, okay, we know that this is a movement into the accumulator EAX. The equivalent is FLD constant. Constant is a variable here, no, which is actually by default. Before we do that, let us head over to our variables. By the way, we have to change the types before we continue. I forgot that. No, okay. I'm sorry. So first we have to transform score into a floating point variable. We do that by saying score as real 4 and we assign it an 80. But this time we have to put a decimal point because it's no longer an integer. It doesn't matter how many zeros you indicate as long as at least you have one. Items is also a real 4. So we make this 0.0. And constant is also a real 4. Do not forget to put the needed decimal point because Visual Studio will complain, will issue an error on this. Base is a real 4. Grade result is a real 4. Because grades will have decimal places, and we do not assign it a value yet. The variable passing is a DWORD because it only stores 1. The variable is also a DWORD because it only stores 0. Cutoff is a real 4, and it's 75.0. And our decision, okay, is which is whether passing or failing, we call result is also a DWORD because it can only be either 0 or 1. Let us go back to our translation. Okay, we have already moved constant to the FPU, and then we convert sum. We do that by saying f sum base. I do not delete the line to indicate the equivalent. And then mul score is done using f mul score. I also retain the line there to indicate that it's the equivalent of the ALU. Div items is done using f div items. Okay, so we are converting from ALU to AFU. So right away we know that we can convert this as f add base. And then this is a store, okay, from the accumulator to a variable. So we are going to use the equivalent command, which is fstp grade result. What happens is that the result in the FPU, which is the grade, is transferred into the variable grade result. Remember grade result here is already a real 4. Now, noting that fstp is a destructive store, we will have to do fload again, fld grade result. Why is that? Because the previous grade result was removed from the FPU, and therefore we cannot do a comparison, which will follow. So that's important, no? Because the previous value of the FPU has been removed by FSTP. CMP is converted into FCOM cutoff. That's the equivalent. Now our problem here is we do not have an FJAE. Remember earlier I have indicated that JAE works only with the ALU, not the FPU. Unfortunately, we do not have an FJAE. So therefore, we have to synchronize our ALU flags with our FPU flags. We do that by FSTSW, AX, and SAHF, which means now that the ALU flags are the same as that of the FPU flags, which will make JAE workable. Okay? And we do not have to change this because we only use dWORDs for result, then we exit the program in the finish location. Now, in order to trace this, it's useless to go over each line of the FPU because we could not trace the values of its accumulator or the FPU stack. What we do is we will put breakpoints, no, in the second line and breakpoint in after F grade result. So we will know what the grade result is. And then lastly, we will go into, we will put another breakpoint before the exit process. Okay, and now we are ready to trace this. Let us do that. We click local Windows debugger, wait for a while. Obviously, if this may have an error, there will be few of them. There's no error, fortunately. And we have our registers box and our memory box. If you look at our registers box, EBX is already set to 1 because we have specified EBX to receive the passing variable, which is 1. And we have move result of EBX into, or rather EBX into the result variable. Let's look at the result variable. We head over to our memory box and type and result, which is the name of our variable. Okay, so this time it's 0. Result is 0. We can also change this to, for the moment, I think the 4-byte value will work. This is 0. Okay. Now we will skip over the lines f init, lb, f sub because it's useless. We cannot trace the value, the registers. However, we can trace the variables. Anyway, the grade result will change on the next breakpoint. So let us just continue. And then uh, the result has changed to 1 because it's moved from EBX. But we are interested in looking at grade result, which is the value that stores the result, the resulting grade. It's in hexadecimal. So we change the format of our memory window by right clicking and then going over checking to the 32-bit floating point. And we know that this is now 88. And if this is our cutoff, 75, and this is the non-zero value, this is 1. This is the passing variable, and this is the non-zero value, which is 1, which is our assumption of the grade. To shift to 4-byte integer, we can right click and then click 4-byte. We know that this is 1, okay, which is the passing value. And let's head over to our result. The result is 1. Okay. So now let's move to the to the next breakpoint. Let's click continue. In the next breakpoint, the result is still 1. And the grade result is still, we'll head over and is still 88, which means that the resulting grade is 88 and it's passing. Okay, and then let's click the final continue to finish the trace. Let us test this to a value which is failing. For example, we know that 50 is a failing score. And then let's run it again. Okay, and let's look at our grade result and switch this to 32-bit. It's already 32-bit floating point. Let us move directly to the next breakpoint. Okay, we know that the grade is 70, but it's still assumed to be passing. Okay, and then let's switch this to 4-byte integer so that we'll know that and look up the grade result. This is the that looks the result. However, we know this to be 1, and then we continue to the breakpoint, the next breakpoint, which is our last, and we know that it has changed to 0. That is because the grade 74 is a failing grade. Okay, so I hope that brings you to the end of this video. I hope you understand this, and we'll be able to distinguish between using the ALU, and the FP. In your other courses later, you will be doing assembly language programming using prompts and inputs, during which you will be able to uh, get values from your user. For the moment, we have demonstrated the use of the FPU. And if you have questions, you can leave a comment below. And if you like, you can click the like button. Or if you don't, you dislike, you are also free to do that. As of the moment, thanks for watching this video, and bye for now, and see you in the next succeeding videos. Bye everyone.